Welcome to session number 6. In this session, we'll be looking at the Fermi-Dirac distribution. We'll be combining semiconductors, talking about the law of mass action, and ending up with an example which will hopefully tie all this together. But first, a marvelous video clip from the movie Carousel. 1956 tells the story of Billy Bigelow, who was a barker in a carousel, tracks all the young women, falls in love with Julie, they get married, and he's a terrible husband. He beats her, he's cruel to her, until Julie tells him that she's going to have a baby, and then he realizes he must change. He conspires to commit a robbery, is caught in the act, but rather than be taken to jail, he commits suicide, goes up to heaven, and after 16 years, he's allowed to come back to earth for one day to correct the wrongs that he's done. He comes back, and he's allowed to be seen by his daughter Louise, tries to give her a star from heaven. She rejects his gift, and she does the only thing that he knows how to do. He slaps her. So far doing terribly. He's asked for one more chance. That request is granted. He now becomes unseen. He goes to the graduation of Louise, and as Dr. Selden is speaking, he goes over to Louise. She can't see him, but she feels his presence. Believe him, darling. Believe him. He succeeds. He comforts Louise. He goes over to Julie. Know that I loved you, Julie. And then he returns to heaven. Mission truly accomplished. We'll see you back in a few minutes.
Miss Louise Bigelow. Our speaker this year is the most popular, best beloved man in our town, Dr. Selden.
He reminds me of that fella up there, that star keeper.
Yeah. A lot of these country doctors and preachers remind you of him.
It's the custom at these graduations to pick out some old duck like me to preach at the kids. Well, I can't preach at you. I know you all too well. I brought most of you into the world. Rubbed liniment on your backs, poured castor oil down your throats. I only hope that now I got you this far, you'll turn out to be worth all the trouble I took with you. I can't tell you any sure way to happiness. I only know that you've got to go out and find it for yourselves. You can't lean on the success of your parents. That's their success. And don't be held back by their failures.
Listen to him. Believe him.
Makes no difference what they did or didn't do. You just stand on your own 2 feet. The world belongs to you as much as to the next fella, so don't give it up. And try not to be scared of people not liking you. Just you try liking them. And just keep your faith and your courage, and you'll turn out all right. It's like what we used to sing every morning when I was a boy at school. Maybe you still sing it. When you walk through a storm, hold your head up high.
You know that one?
And don't be afraid of the dark.
Believe him, darling. Believe.
At the end of the storm is a golden sky, and the sweet silver song
Julie. Know that I loved you.
Okay, these are the topics we'll be covering today. We're going to have a short review. We'll be looking at salt water and donors and tying those two to their respective energy band diagrams. We'll be attempting to give an intuitive derivation of the Fermi-Dirac function, and we'll ask the question, what does the Fermi-Dirac function give us? What's the result? And we'll find that the result of the Fermi-Dirac function is the probability of occupancy. So we want to talk about what is electron occupancy and how does it relate to ionization. And we'll see sometimes they're the same, sometimes they're opposites, and that's a big deal. Then we'll be looking at p-type semiconductors and acceptor atoms, a bit of review, and just to strengthen our comfortability index in p-type as it's differentiated from n-type. P-type are acceptors, n-type are donors. Then we'll be combining semiconductors, combining salt water and clear water, and we'll see what happens in that case. And then we go on to the law of mass action and the Chatelier principle, which I hope you've been exposed to it a little bit in your basic chemistry course, but we'll be reviewing that and seeing how that relates to semiconductor devices. And then we tie it all together with an example from a midterm. I believe it's from McGill University. So let's take a deep breath and get started. Okay, so here is the part of the periodic table. Column 4 has carbon, which is the lightest, the largest band gap at 5.5. When I say carbon, I'm really talking about crystal carbon or diamond. Silicon is heavier, smaller band gap, 1.1 eV. Germanium, heavier yet, smaller band gap, 0.67. And tin, the smallest yet. Germanium and tin we're not particularly interested in. We will have an interest in germanium when we combine it with silicon to form something called silicon germanium. Okay, so now we have phosphorus, which is in column 5. It has 5 electrons in the valence shell. It can donate 1 electron to silicon. And when it donates an electron to silicon, it was neutral. It gives up something negative, so it becomes positive. On the other side, we have boron, which has 3, which can accept an electron from silicon. The silicon now has a hole, which is positive, so the silicon becomes p-type, P for positive. The boron becomes negative. Both negative boron and positive phosphorus are fixed ions in the lattice, and that is a really big deal. And that's a difference between ion implanting phosphorus and boron and mixing salt with water. In salt water, both of the species, sodium and chlorine, are both mobile. In ion implantation, we create mobile electrons for donors and fixed positive phosphorus ions in the silicon lattice and fixed negative boron ions in the silicon lattice. These guys, the boron and the phosphorus, they're ions, but they ain't mobile. Okay, so now we have this. This is from last session. Not particularly important. You might just want to review some of these differences and make sure you're comfortable with that. The whole idea in dissolved salt water is to gain a level of comfort. That's the only reason why we had it at all. Okay, so now let's go back, or let's go forward to the energy band diagrams. In this salt water case, we have two mobile ions, sodium positive, chlorine negative. There is a driving force for ionization. We have the state of the water, or the chemical potential, and as we dump in more and more and more and more salt, the chemical potential rises and the probability of ionizing becomes less and less and less. Same thing for implanting phosphorus into silicon, a donor. The Fermi level for donors is above the intrinsic semiconductor. The Fermi level is analogous to the chemical potential. There again is a driving force, and as we dump in more implanted phosphorus into the silicon, the driving force becomes less and less because the Fermi level goes up and up and up. The distance between the conduction band edge and the pure silicon does not change. That is only a function of the material. What changes is the state. And as the Fermi level rises and the ionization driving force decreases, the probability that the electron stays on the phosphorus atom becomes greater and greater. And that's indicated here too, where we have the complete electron energy band diagram, and here the positive arrow indicates that we are, positive up arrow indicates that we're dumping more and more phosphorus into the silicon lattice, and the ionization driving force becomes less and less. Okay. Now let's see what happens if we have a certain amount of electrons in the conduction band due to implanting of phosphorus. That's why the Fermi level is above intrinsic. This looks like about, well, the whole thing here is about 0.56, because from here to here is 1.1, so half of 1.1 is about 0.56, and this looks to me to be about 0.2, and I can tell you 0.2 eV would be about 10 to the 15th. The driving force now for implanting donors is the distance from the Fermi level to the phosphorus energy state. It's this distance right here. The driving force for implanting boron, excuse me. The driving force for implanting boron is that from the Fermi level to the boron acceptor level, and you can see that it's much, much larger. So if the probability here of ionization is pretty high, the probability here for implanting boron is really, really high. And that's what that diagram is meant to illustrate. So now we come to a rather important distinction, the distinction between occupancy and ionization. Okay, so if before we took a deep breath, now let's take 2 deep breaths. The issues are not particularly complex, but there's a lot of them, and we have to sort of reconcile all these disparate facts. Let's start with phosphorus, P. Occupancy means that the donor electron is orbiting the atomic nucleus, which means, that is, that the phosphorus atom has not donated its electron. The electron is still with the phosphorus. If we go back here, it has not jumped up. The electron is still at the donor energy level. For an acceptor, it's the exact opposite. For an acceptor, it means that boron has accepted an electron from the silicon lattice. Where's the electron? It's on the boron. The electron's on the boron, and it leaves behind a mobile hole. The boron, with its electron, is fixed, not going anyplace. The phosphorus is neutral if it's occupied by an electron, and of course, it's not going anyplace. Now, how does that relate to ionization? In the former case, the atom, case up here, where the phosphorus atom has not, I emphasize the word not, donated electron, is not ionized. It's neutral. The number of protons equals the number of electrons. For boron occupancy, the boron is ionized. It has more electrons than protons. Now here's the kicker. The Fermi function gives the probability of occupancy, not of ionization. They can be equal in the case of boron. They can be mutually exclusive, as in the case of phosphorus. Occupancy and non-occupancy are always mutually exclusive, as are ionization and non-ionization. Thus, the probabilities add. What do I mean by mutually exclusive? Flip a coin. Probability of heads, 1/2. Probability of tails, 1/2. They're mutually exclusive. You can't have heads and tails in the same coin toss. Flip or throw a die. You got 6 possible numbers that can come up. They're all mutually exclusive. You cannot have a 3 and a 6 coming up at the same time. Each probability is 1/6. The total, if I ask the question, what is the probability that one of those numbers will come up? It's 1, because one of the numbers has to come up. 6 times 1/6 is 1. For a coin toss, 1/2 times 2 is 1. 1/2 plus 1/2, heads and tails. Because they are mutually exclusive, the probabilities add. Now this is summarized in this rather important table, much more important than the other table, which compares salt water to donors. For an N-type, the Fermi function gives the probability of occupancy. It always gives the probability of occupancy. But the probability of ionization is mutually exclusive to the probability of occupancy. So the probability of ionization is 1 minus the probability of ionization. In P-type, the probability of occupancy is still given by the Fermi function. Notice now it's EA, which is the acceptor level, rather than ED, the donor level, and the probability of ionization is given also by the probability of occupancy, because if the ion, or if I should say the atom, the boron atom, is ionized, the probabilities of occupancy are given by the Fermi function. Therefore, the probability of ionization is given by the Fermi function. As the dose of phosphorus increases, the Fermi level rises, and the probability of occupancy goes up, and the probability of ionization goes down. As the dose increases for acceptors, the probability, or the Fermi level falls away or goes down, and the probability of occupancy goes down, and the probability of ionization goes down. So, try to follow the logic. I hope it's right. I think it is. I make mistakes a lot of times. If I had a nickel for every time I heard this explained incorrectly, I would be quite wealthy. Okay, so now let's look at an intuitive derivation of the Fermi function. Again, the Fermi function is a probability, thus its range is between 0, 1, which is impossible, and 1, which is 100% certain. That's the definition of probability. The Fermi function involves the difference between the Fermi level and the donor state or the acceptor state. This difference right here, the driving force between the Fermi level and either the donor state, which is this distance here, or the Fermi level and the acceptor state, which is this distance here. We're going to call that, I think we call that delta E. And what we're saying here is that as this delta E decreases, gets smaller and smaller, let's say for donors, that's why we have ED, then the probability of occupancy goes down. The driving force goes down. The probability of occupancy goes down. We are thus tempted to write the probability first as an exponential, because everything is going to be exponential, and it should be minus delta E in the numerator. Well, we can't have just delta E in the numerator because this would mean that this whole thing has units. Can't be. It's got to be dimensionless. So we divide by KT, just like we do all the time, to make the units come out right. So the probability doesn't have units, and it's just a number between 0 and 1. And writing that explicitly, this is delta E. We just substitute for delta E. This is for donors. Well, this has to be a probability. Maybe. It's almost a probability. If delta E is greater than or equal to 0, it is a probability, because if delta E is 0, E to the 0 is 1, and as this number gets smaller and smaller, the probability gets less and less. So it eventually goes to 0 if this number is extremely large. However, the Fermi level could actually, in principle at least, be greater, be higher up than the donor state. In that case, this is not a probability anymore because it has a magnitude of more than 1. That's not good. So how do we fix it? We fix it simply by adding a 1 in the denominator and making the inverse, and this collapses to this thing, which is called the Boltzmann approximation, if delta E, ED minus EF, is greater than about 3 KT. And remember, KT is about 0.026 EV at room temperature, so if delta E is greater than that, this thing basically collapses to this. And this is one that we will use all the time. This is called the Boltzmann approximation. Okay, now let's look at a comparison of combining two salt solutions with different levels of salt concentration with combining two samples of semiconductor materials. I'll use silicon generally when I talk about semiconductor materials that have different doping levels. So in the two salt solutions, we're talking about different chemical potentials, and in the two semiconductor samples, we're talking about two different levels of Fermi level. So first talk about a salty solution. Chemical potential is close to saturation, and here we have just a little bit of salt with a chemical potential close to pure water. Well, we know what happens. The salty water gets less salty, the pure water, or the water which has less salt, becomes more salty. Pretty straightforward. Does it have any practical application? You bet. And here I'm going to have to apologize a little bit, because quantitatively it works out that the chemical potential of pure water is the highest chemical potential. It's almost like P-type semiconductors. So it's way, way up here for pure water, and it only goes down. But the idea is the same. The idea is that chemical potentials equilibrate. Salty gets less salty, more salt. The less salty gets more salty. Application, well, if you put a blood vessel, for example, in pure water, what happens is you'll find that not the blood vessel, a blood cell, sorry about that, a blood cell in pure water will burst. What happens is that the water, pure water, will flood the cell, and it will cause it to have so much pressure that it will just explode. The same thing happens when pure water comes into a tree or a bush, or finds a little chute, a little vessel, a little conduit, and what happens? It goes up. Sometimes it can go up hundreds of feet in the air. And what's happening is that the pure water, rainwater, meets contaminated water, or water which is not pure, in this little vessel, and the two try to equilibrate. That's called osmosis. It requires no sunlight, no energy, and without it, life on Earth would not be possible. So that's a big deal. Quantitatively, I'll let you study a course in biology to figure out how that works, but the idea is the same. Okay, what happens when we put two samples of silicon together? Let's say an N-type silicon which has phosphorus positive ions, and a P-type which has negative boron ions. Well, again, the Fermi level on the P-type goes up, the Fermi level on the N-type goes down. Electrons flow from N to P, and holes flow from P to N, uncovering these ions at the interface. And wherever we have ions, we have charges. So there is a positive charge on the N side, and there is a negative charge on the P side, and that produces an electric field. Electric field means that we have a potential difference of voltage. So we have a little battery right at the interface, and that is exactly how all semiconductor devices work. We have a barrier right at the interface, and that barrier can either be reduced, that's called forward bias, or it can be enhanced, called reverse bias. Both are critical to the operation of all semiconductor devices. So this is from the text. I'll let you read that. This, I believe, is in chapter 3. So we'll skip over now to the law of mass action. Okay, so now let's talk about the law of mass action, which is an incredibly important law for semiconductor materials, and we're going to try to explain that using the Chatelier principle and the principle of equilibrium chemical reactions. So you may be wondering what happened to the thermal excitation of electrons even if there is no doping. Remember that this exponential tail in the Boltzmann distribution had some really, really energetic lattice vibrations or particles or whatever, and they're able to kick an electron up from the valence band into the conduction band. And remember, that's why we said silicon is maybe pure, but it sure ain't perfect. And there's about 10 to the 10th electron hole pairs created at room temperature, given by this rather formidable expression here. This is quantum mechanical. We'll derive this, I believe, in chapter 5, or it is derived in chapter 5. I don't know if we'll be able to do that here, but it's the derivation is carried out at least in chapter 5, or in some textbooks, not all. Many of them just write it down without deriving it. So let's use an analogy to salt water. Salt breaks up into sodium and chlorine, and it is a reversible reaction. Unlike silicon, which reacts with oxygen to form SiO2, also known as glass, which is not reversible. It's only one way, from left to right. Silicon plus oxygen gives us SiO2. Here, the salt can go out, the salt ions can come back into salt molecules, depending on the temperature and how much salt we put in. In general, if we have, these are not, this is not silver and this is not boron, this is just A, B, C, D. So if we have a equilibrium chemical reaction, we define an equilibrium constant, which is just equal to the products, the molar concentration of C multiplied by the molar concentration of D, divided by the product of the molar concentration of the reactants A and B. Well, let's use that to look at the reaction of silicon at equilibrium, producing electron hole pairs. Nothing to do with doping yet. We're going to get to doping in just a little bit. But right now, this is only thermal excitation. But it's the same thing. Product of reactants divided by the molar concentration of silicon. So it's an equilibrium reaction coefficient, product N times P divided by the concentration of silicon lattice atoms. This is something we actually calculated in the last session, which is precisely why we did that. And you may recall that it is 10 to the 22. What is N? 10 to the 10th. What is P? 10 to the 10th. They always must be equal if there's no doping. So we just put that in, and we find that the equilibrium chemical coefficient, equilibrium reaction coefficient, is equal to 10 to the 20th divided by 10 to the 22, or 10 to the minus 2. Now, here's the trick. We're going to dope our silicon lattice with lots and lots of electrons. We put in a huge dose, not a huge dose, a relatively large dose of phosphorus. It ionizes, and let's say, I believe I said that this was 10 to the 17th. So N now has jumped up from 10 to the 10th to 10 to the 17th, and I want to find out what the P is. Well, the reaction coefficient hasn't changed. It's still 10 to the minus 2. The silicon lattice number of atoms is 10 to the 22. So what we find is that the concentration of holes is 10 to the 20th, 10 to the 22 times 10 to the minus 2 is 10 to the 20th, divided by the new N, which is 10 to the 17th, due to phosphorus doping of 10 to the 17th phosphorus atoms per cubic centimeter, and every one of those bad boys is ionized, and we find that in this case the number of thermally generated, and I emphasize the fact, thermally generated holes goes down to 10 to the third. Was 10 to the 10th, it goes down by 10 to the 7th to 10 to the third. And you say, well, that's a little bit. Well, that 10 to the third it's pretty important. So that's why we take some time in actually calculating it, and it's quite a big deal. It's quite a big deal. Now, let's say we raise the temperature so that the equilibrium coefficient, reaction coefficient, is not 10 to the minus 2, but 100. We could do that by, for example, raising the temperature to probably about 400 or 500 degrees Celsius. So many more lattice atoms are thermally excited, and then we still put in the same 10 to the 17th. Well, for the mobile electrons. So now we have 10 to the 17th mobile electrons. We want to find P. The number of silicon lattice is still 10 to 22. That hasn't changed. But the K, instead of being 0.02, is now 100. And now we have P is 10 to the 7th. So at an elevated temperature, it only depends on the temperature, the law of mass action can be quite different. But in both cases, the number of mobile electrons, or I should just say the number of electrons, we assume all electrons are mobile if they're in the conduction band, multiplied by the number of holes is equal to Ni squared. Ni squared for room temperature is 10 to the 10th times 10 to the 10th is 10 to the 20th. And if the number of electrons is 10 to the 17th, the number of holes is 10 to the third. Okay. Now, a final word on charge concentration and neutrality. We're still doped. We're doped to 10 to the 17th. The number of holes is 10 to the third. And they're all thermally generated. What is the total number of electrons? Well, it's composed of two parts, the external part and the thermal part. The external part, the doping part, the phosphorus contribution is 10 to the 17th. The thermal part is 10 to the third. Why is it 10 to the third? Because the thermal excitation comes only in pairs. For every hole generated, there is an electron generated. For every electron generated, there is a hole generated. So the number of electrons is 10 to the 17th plus 10 to the third. Well, this is so small compared to 10 to the 17th that we generally neglect it. Okay, now we go to a problem, and the problem is from a midterm exam from a semiconductor device course. I don't know if this is graduate or undergraduate, I'm not really sure. It doesn't matter, they're all the same. And you can be sure that a problem like this will appear in every single course that you can ever imagine taking in semiconductor devices. Same thing, guaranteed. So if you know it, you just write the answer down, which is cool. Okay, so you're given a silicon sample doped with 10 to the 15th, which is a very light doping today, of arsenic atoms per cubic centimeter. And it's under equilibrium conditions. We'll have to talk about that a little bit later. Nothing's happening. It's just doped. And the first question asks, are we talking about donors or acceptors? Well, if you go all the way back to the periodic table, it works out that arsenic is a donor. So donor means, remember the two big donors are phosphorus and arsenic. The big acceptor is boron. I think they do this just to be absolutely terribly nasty. I mean, they really probably should have said phosphorus, because phosphorus is the default situation. So they're trying to put a little asterisk in there. I think it's disgusting, but that's just me. All right. They want you now to draw the energy band diagram at a very low temperature. This is Kelvin, 77 Kelvin, 300 Kelvin, which is room temperature, and at 600 Kelvin. And you're asked to show the Fermi level and the intrinsic as the reference level. And let's just do that very quickly. It's 77. The Fermi level is way close to the conduction band. At room temperature, if it's 10 to the 15th, this would be about 0.1, off the top of my head, that's about 0.15, 0.16, I'm not really quite sure. And at 600 degrees Kelvin, it is closer to intrinsic. And that's exactly what we'd expect, because the higher the temperature, the easier it is to donate electrons, and the higher the driving force. Where's the actual donor state? It's way up here. It's closer to the conduction band, very close to the conduction band. So it's between this level, Fermi level 77, and the conduction band edge. Okay. Now at 100 degrees, or actually I didn't like 77 because 77 is so cold that other things happen. So I arbitrarily changed it to 100 degrees. Shame on me, but I did anyway. We're way up here with the Fermi level, and the number of mobile electrons, or number of electrons, is approximately equal to the number of donor atoms, because this Fermi level is still probably about, I don't know, 3 or 4 times kT. So the number of mobile holes is quite small. Well, what would it be if the number of mobile electrons, or electrons, is 10 to the 15th, because all of the arsenic, not phosphorus, all the arsenic atoms are ionized, the number of holes is about 10 to the 5th. I shouldn't have said very small. It's small. At 300 degrees Kelvin, the Fermi level has dropped, and I shouldn't have said N is still equal to ND. It's even more equal to ND, because here it's certainly ionized. Every one of the arsenic atoms is ionized, so we have 10 to the 15th arsenic ions, 10 to the 15th electrons in the conduction band, and the number of mobile holes is 10 to the 5th. And however, here it's a little bit different, because it's 600 degrees. At 600 degrees, even though all of the arsenic ions are ionized, the number of thermally generated holes is equal to the number of thermally generated electrons, and it's much greater than ND. I don't know what the number is off the top of my head. It doesn't ask for specific numbers, but I suspect it's 600 degrees, 600, is it Kelvin or centigrade? Oh gosh. Oh, Kelvin. 600 Kelvin. This may be 10 to the 16th or 10 to the 17th for both of these guys, which is greater than 10 to the 15th. So that's all the problem asks for. And anything qualitatively close to that, you would be expected to get full credit. Okay, we end with the finale from the movie Lilium. And remember, we saw the finale to the wonderful Broadway show Carousel. Now we're going to look at Lilium, and I just would preface this by a statement. It is said that the gates of justice are very rarely open. The gates of prayer are sometimes open, sometimes closed. The gates to tears are always open. The Broadway production of Carousel was taken from a play by Frederic Monet, and it's called Lily-Om. And instead of Billy Bigelow, Carousel, Billy becomes Lily-Om. But he's the same person. Julie is his wife, who he acts very cruelly to, and his daughter Louise, he comes down from heaven, sees her for the first time in 16 years, becomes visible to Louise, tries to give her a star from heaven. She rejects his star, and he does what he only knows how to do, and he slaps her. And when he slaps her, the scales of justice tilt toward justice. And then he goes back up to heaven, and he stands before the heavenly court, and the heavenly judge is going to sentence him to an eternity in hell, and then something wonderful happens. And let's look at the finale to the marvelous movie Lily-Om. I believe it's 1933 or 1934, with a very young Charles Boyer. And we'll see you next time.
Encore vous? Comment êtes-vous entré?
Mais, mademoiselle, je vais vous expliquer.
Laissez-moi. Allez-y.
Oh, je suis venu de loin, de si
Je
loin.
ne veux rien écouter.
Mais mademoiselle, oh, j'aurais tellement voulu faire pour vous quelque chose de beau, de très beau.
Non. Allez-vous-en. Tout de suite.
Mademoiselle.
Allez.
Oh, lâchez!
Guillaume, 16 ans de purgatoire n'ont pas suffi pour consumer ton orgueil et ta violence. Incorrigible, absolument incorrigible, tourmenter le cœur d'une enfant qui te gardait son amour d'enfant. Qu'as-tu à ajouter pour ta défense?
Qu'elle m'aimait tel que. Pourquoi vouloir me faire meilleur que je suis? Alfred avait raison. Pour nous, même au ciel, il n'y a que la justice. Rien que la justice.
Et cette justice de...
Maman. Maman, quelqu'un t'a-t-il déjà donné un coup? Mais un coup fort, un coup qu'on entend claquer, sans que tu aies rien senti.
Oui, mon enfant. Quelqu'un m'a déjà donné un coup. Et je n'ai rien senti.
Est-il donc possible, maman, qu'on vous frappe sans vous faire aucun mal?
Oui, mon enfant. Il est possible que quelqu'un vous batte sans vous faire aucun mal.